All right. So the type of the nuclear fusion which we need, as we explained, is the one which started by light elements. If you want to produce the energy with heavy elements, the process will be the one which is happening in nuclear reactions. If you have any question, please turn on the microphone and talk to me, because I cannot read your messages when I am in the slide. So I told you, if you want to make any nuclear reactions and get the energy from heavy elements, instead of the fusion, you have fission. Fission is the effect which is a type of the chain reaction which is happening in nuclear reactions, in the nuclear reactors, and basically is the same as the process as happen in nuclear bomb. In that process, which is called fission, to gain the energy, we will start it by heavy elements like uranium, like plutonium, and then by chain reactions, this heavy element is breaking to the lighter elements, and during this process, some energy will gain. And you can use this energy, as you know, for the thermal reactors, for nuclear energy in the military systems, and so other things. There is a difference between fission and fusion. That difference is not only because the fusion can happen with light element and fission with heavy element. The difference between these two processes is that the fission reactions will start only if the mass of the heavy element reach a specific amount of the mass. So this is called critical mass. I mean, you can have a uranium, but not any uranium can make for you the fission reaction, or plutonium. So you need the critical mass. Yeah. But for fusion, which is happen inside the star, there is no such critical. There is another parameter similar to the critical mass in the fusion process. That is the temperature. As you remember, temperature should rise up to the special limits for the fusion to be started. How nuclear fusion works? So imagine you want to make a fusion reaction with two deuterons. So deuterons are, you know what is the deuterons? Anybody know what is the deuteron? This is a type of the deuterons are the atoms which they comes from the tritium nuclear, and it has a one hydrogen and one and the atomic numbers of the the atomic mass of that is different from the atomic mass of the hydrogen. So it's almost the same as hydrogen, but it's called the light hydrogen. So two deuterion can make a fusion reaction. They combine each other, and then it gives you the helium-3 and one neutron. The energy which we release during this process can be calculated, as I will show you later in the next slide. To calculate the energy, you have to sum the masses on the left side and subtract the sum of the masses on the right side. The difference between the mass will give you the energy which will be produced during this process. So you have a two deuterium. So each deuterium has the mass of 2.014 atomic mass unit, which is called AMU. So you have two of them in the left side. So And the mass of the right side, you have one neutrino, you have one neutron, sorry, and you have one hydrogen 3. So each one, you have their atomic mass. The atomic mass of neutron is 1.00866 atomic mass unit, and the helium-3 weight as 3.015 atomic mass unit. So the total mass of the left side is 4.037, as you see, and the right side is 4.0237. So if you subtract the left from the right, then you will find a difference of the mass of 2.209 10 power minus 29 kilogram. Here I just write the atomic mass unit in terms of the kilogram. Therefore, now you need the Einstein equation. So the equivalence between mass depth energy gives you that during any process, any change or difference in the mass leads to some amount of the energy. So you have a delta m here. So if you just substitute delta m along the speed of the light, so finally you will get the energy, which is 6.627 10 power minus 15 joule. And if you wanted to combine this, you can write it this energy in the terms of the units of the other units of the energy also. But I want to tell you that this energy is a lot of energy actually. In the next slide, you see that in the fusion, actually, as you see, so deuterium, this is a deuterium, this is a tritium. So from tritium, so deuterium comes from that. So then these two deuterium, which they are very fast particles, they collide here. As you see, they will collide. And then during this process, some energy will be released. I want to tell you that the energy which released here is 676 units. And this is a big energy because 1 unit is the energy which one American, for example, citizen approximately use in 1 year. So just by one fusion reactions, you can fit around 670 persons energy for 1 year. So that is the reason that why the nuclear reactors, and generally speaking, extracting the energy or producing the energy from nuclear reaction is such importance, has such importance for the people. All right, we talk always about the particle will collide to each other and whatever. So when two particles are collided to each other and make a collisions, so it's called interaction. So such process we call interactions. And interactions mainly could started by the two particles. As you see, two deuterons started the first interaction, for example, in the nuclear fusion reactions. They permit for any type of the nuclear reactions, this process permits. Cross sections means that when two particles collide, so how much will be the area of the, I mean, for example, some particles, for example, I want to say first the cross section is, we are meaning geometric cross section. What is geometric cross section? Geometric cross section for a type of the interaction between particles, which we are talking very tiny particles, is that like you throw the balls to the targets. So if you're shooting a target by gun, for example, the number of the bullets which is targeting your target, or which is colliding with your target, gives you the number of these bullets which you shoot, and they hit to the target. This is make a sample on your targets. So as much as you shoot more bullets in the short period to the one target, so you will have more effect of the bullet on your target. You can say that the cross section is more. So anytime when you want to talk about cross section, remember what I told you, that shooting the gun and the number of the bullets received by the target is a measure of the cross sections. The problem here is that when the particle want to enter the fusion reactions, before they start the fusion or even during that, they will collide with each other. So you will have something called reaction cross sections. Reaction cross section is a geometric cross sections, is the geometric cross section multiplied by the reaction probability. What does it mean? You shoot a target by your gun and you shoot that with 50 bullets per minute, the targets. But remember that the bullets can shoot everyone independent from the other one. I mean, when you shoot the first one, then by pressing the second and third, so they will be shoot to the target, yes? But consider now, instead of the bullet, consider the particles. When the particles are shooted to your targets, the things which happen is that some of the particles maybe make interaction, yes? So you have to exclude the number of the particle which before they receive by the target, they will make interaction. This is called a reaction probability. So reaction cross-section is the usual geometric cross-sections. I mean the area of the target which is targeted by the bullets multiplied by the reaction probability. Reaction probability is not a big number. It's just maybe 0.1% or even 0.2%, and you will see why. You will see why this probability is not very big. I will go to explain what is the cross section, but before I want to one more time talk about the units. So when we talk about the targets or interaction between the particles, you have to remember that the size of the target, I mean the size of the interaction or the distance between the particles which they make interactions is very, very tiny. Basically, in atomic nuclei are very small in atoms, and the radius of atom nuclear is 10 power minus 15. This is called 1 Fermi. Their cross section is just like area. Area is proportional to the radius square, so cross section is 10 power minus 15 power 2, 10 power minus 30. You remember, so what does it mean? It means that you are standing in the front of the target and the size of target is 10 power minus 30 meters square. Okay, and you're shooting that with the particles instead of the bullet. Nuclear physicists don't use it 10 power minus 30 or something like that. They define it 10 power minus 28 meters square to be 1 barn. So the usual cross section is 0.01 barn. So nuclear cross section are typically measured in unit of millibarns, microbarns, or whatever. There is a paragraph here about why they call it barn. You can read it yourself. Not only that, there is another thing here which is very important. This is not only about the size of the target, also about the number of the particle which they are involving in these interactions, in this process. Let's see, I am checking that everything is fine or not. All right. The number, density, and mass fraction. So as I told you, this is not only important that what is the size of the target which particle will attack that or touch that. It is also important to know that how many of those particles are colliding or are attacking this targets. So we are defining something called number density. Number density is the number of the particles. If you have a different particle, it is not all the particles are not deuterions. So I mean, the fusion never been considered as a nuclear reaction only made by the deuteron. So you can have other any elements, any lighter element with the mass below the nickel. So what is we call it number density for any particle of type I is given by Ni, and it is just simply defined as a number of particles on that time per volume. Number, for example, it's like Avogadro number, so the volume is, you see that the volume is very tiny numbers. So number density, which is called N, is actually 1 per volume. So the unit of volume is m cubic, so the unit of number density is meter power minus cubic. The mass density, that was a number density. What is the mass density? The mass density is the one which you know in the fundamental physics. The density of any object is given by mass over volume. Yeah. So if you have some particles which we label this particle by I mean the particle of the type of I, they have the mass of mi here. Then you have to divide this mi by volume and multiply that to the number of particles which you have. But as I mentioned before, the number of particles per volume is already defined as a number density. So the density of mass will comes like Ni times Mi. And if there is a mixture of the particle, I mean, if you have more than one type of the particle, it is very interesting and useful to use a parameter we call it number fractions. So number fraction is defined as a number of the particles in the type 1 over the total number of the particles. What is the benefit of them? Because we will use them to define the probability of the collisions. The mass fraction is the mass of each type of particles. So if you have a j different type of particles and each one has a density of the number Ni and mass of them is Mi, so then the mass fractions of each particle can be defined as, for example, for particle number 1 will be N1 My over sigma NIM. This is like an average. For any collision of the particle, you can define this parameter like particle density, mass fraction, and whatever. Okay, if you combine those definitions, there is a possibility to write the number density in terms of the mass fractions and the mass of each element and the mass density. If you define the mass density by rho, and if you show the mass fraction by xi, and if m is the mass of each element and n is the number density of that special element, then you can get the equation 3.10 just by combining the equations which I show you already in the previous slide. Okay, now we are going to explain the probability of reaction. You see that we talk about reaction cross sections. We say that the reaction cross sections is given by the geometric cross sections, I mean the area which the particle hits the target, times the probability of the happening any type of the reactions before the balls reach the targets. to make a model for probability of reactions, we say that we consider a target, and this target has n particles per volume. So number density of the target is n. If the particles attacking or incident number of the particle to the targets are coming after traveling a distance delta x, then the probability of the interaction is given by this expression. This is a definition of probability of interactions. So you have a sigma here. Sigma is a geometrical cross sections. N is the density number of the particles on the targets. And delta x is the distances which is traveled by the particle before they attack to the targets. So this is a probability of reaction. So if you want to find the probability of non-reactions, what you can do is, you know that the reaction is happen or not. There is only two possibilities for that. So if a reactions happening with the probability of the given as sigma n delta x, so the probability of not happening the reaction is just 1 minus the probability of happening the reaction. All right. Okay. How many of such process will happen? So it is happening several times. I mean, our discussions is about small distances. As you see, we talk about the probability of reaction just in the small distances before the particles attack to the targets. So if you have a finite distance x, so you can divide the finite distance x to the tiny parts of delta x. So x will be n times of the delta x. Anybody know that what are we doing here? What we are doing here looks like calculating the integrals. To find the area of enclosed by the one function in calculus, you divide that to the small pieces, and you calculate the area of each pieces. Then by summing over all the area, you find the total area. Here what we do is that we are going to divide the distances from the source to the target, which is, we call it x, to the tiny pieces delta x. Then for each tiny piece, you have the probability of the reactions and probability of non-reactions. Because if the particle make reaction, they will destroy it. And the particle cannot reach the target. So you need to know that how many particles survive. Yes? So what you need is probability of no reactions, or call it survival probability. Probability of surviving a particle is probability of the first one, probability of the second, probability, and then you take n exponent. N is very large number because the number of the particle which they are shooting to the target are very large. But this is a very simple model. Then you get the probability of survival. It is exponential reaction. Probability of survival is plotted here, as you see. If the x is very increasing, so if x is increasing, so the probability will decrease, but it never can be 0 because we can never be absolutely sure that it will hit a target. So the survival probability becomes incredibly small. I mean, we never can be sure that a particle can attack the targets, even if it survived after the collisions with the other particles. So this is the diagrams for the exponential of minus sigma n x, the function which I show you in the last paper. All right. This survival probability, or the probability function, survival probability Px, is very important function. if you have this P, then you can calculate so many interesting quantities. One of the quantities which you can calculate is the mean free path. Mean free path, I want to first explain the concept. The concept is that the particles are traveling to reach the target, and they are colliding to each other. They make interaction to each other. What we call it mean free path is the average distance which a particle travel before it goes under the interaction with the other one. Particle A started moving, particle B started moving. Before the particle B collides to the particle A, it moves at least some distances. So this distance is called mean free path. How to calculate the mean free path? To find the mean free path, we consider the probability of the particle which is travel in the short distances between x to x plus delta x. The probability of traveling a particle in the short distance is given by the probability times the distance between the points. So px delta x will be the probability that a particle travels in the short distances. Then if you want to calculate the mean distance means that you have to integrate or sum over the all of such distances which is passed by the particles. The total what we call it mean free path is actually the integral from 0 to infinity, but infinity doesn't mean infinity in the mathematics. It is actually a finite size or the maximum size for your system. I mean the maximum distance between the particle shoot from the source and to the target. L, or mean free path, is given by the integral of xp x dx. In mathematics, the integral of xp x dx is called the first memento. Maybe some of you remember that the concept of the central mass. Center of the mass of any system is the point which you can consider with the total mass of the whole systems located here. So if you remember the physics 1, the center of mass can be calculated as the integral of x times the mass of that point, which we call it density, times dx over the total mass. So this looks like that. I want to tell you that this is the first momentum of the system, mean free path. For mean free path, you need to know the px, and we already know the model for px. I want to explain more about the mean free path. What is the mean free path? So you know that all particles like photons and they are making the interaction. So they are colliding with each other. Not only with each other, also with other particles. So the distance which they travel in this space is very short. This is called mean free path, actually. If the density decrease, if the density of the particle decrease, for example, if you're talking about the particle in the universe, then the universe will turns to something like a transparent system. So the mean free path of the photons can be very large if the density, but the density of the universe is not very low. So basically the photons have a mean free path of very tiny numbers. So I want to combine all in the history. So when the universe is cooled, I mean when the temperature of any stellar system goes below the special numbers, so the free electron and protons, they can finally bond. They will bond each other, make the atoms, and we have a hydrogen plasma. This is a system of hydrogens, and then the mean free pass for the case when you have a hydrogen is very short. But during the radiation times, so this hydrogen plasma turns to atomic hydrogens, and then the mean free pass could be increasing. You can read it, watch this slide is a little more later and read it more. Okay? Then, how to calculate the mean free pass? If the mean free pass, if you consider a model of the n target particles per volume, so Px is the probability of interactions. So you know what is the probability of interactions? Then Px is the probability of survival, as we explain it. You can multiply that to the probability of interactions occur over the interval. I mean, finally, the mean free pass is given just by the integral, as you know, integral of from 0 to infinity of x px. And for px, you have the model exponential minus sigma n x. You remember how we derive these equations? So then you can multiply these, you can calculate these integrals. If you calculate these integrals, for the calculation this integral, it is very easy. Integral of exponential, you can easily calculate it. You have x here, so to calculate the integral of x e minus ax, so you can use the several techniques, but the simple way to calculate this integral is part by part. You can take integral part, or any other methods. So finally, the mean free pass of the particles for a target with the cross sections of the sigma and with number of the number density of the particles on the target n is given by 1 over sigma. So if you want to interpret these results in the, we can say that the mean free pass is the distance which travel by the particle, which they are projectiles. We call it projectile, or projectile means that the particle which you shoot by the gun to the target, always remember. This is the mean free pass is actually the mean, if the average distance is traveled by the projectiles or particles before they hit or before they interact at the targets. And this is given by the 1 over sigma n. Sigma is the total cross sections, reaction cross sections, and n is the number density of targets. The mean free pass is the distance traveled, and you can imagine how much the particles are fast. To know the speed of the particle, you need to know their energy. So you have their energy, you can calculate the speed. When you calculate the speed, and if you know the distance, the average, so you can easily calculate the average time. So the mean free pass will be related to the average time. What time? The time between collisions. And so that makes me very helpful, these questions. Do you have any question? I want to plot just show you that little above the plotting of those functions. So you you expected to be able to plot the functions, but anyway, so you remember that the probability of survival probability was minus 1 sigma. So sigma was the reaction cross section, n was the number density, and x was that. Yeah. And the mean free pass was given by integral, was given by the integral of 0 to infinity of what? 0 to infinity of x probability times sigma n ax. So you can see that the mean distance is 1 over n sigma, as you see. So n sigma will be L. So you can see very beautiful that you can replace it in the P. In the P, you can replace it n sigma by 1 over L. Then sorry, maybe it's not a. Oh, okay. Sorry. Oh, it's okay. This is exponential of minus. I set it sigma. Okay, 1 minute. This is sometimes it's not very clever. The computer is not very clever. Sigma. I set sigma L over N. L over N. So what is the problem? So I see that this is the exponential minus x over, yeah. So this is the mean free pass. This is the mean free pass. And also you can replace it this. I don't know why it's confused here. Anyway. You can plot this function and whatever. So the other things was here in the slide. I say you that you know, we had this quantity when you want to calculate the survival probability. I think let me survival probability. When you want to calculate the survival probability, you end with these expressions. You see these expressions. So do you know how in the limit will be exponential? I want to also explain that. So just it is instructive to say that why you can take a limit of easily you can take a limit of the what? 1 minus sigma n x, sigma over x, sorry, n x power n, and let n be infinity. Okay, the limit will be 1 minus exponential. So this, I mean, this proof which is written here is you can do by computer also. Yeah, it's very interesting. And this is a mathematical, and there are other software you can use it for the calculation. You can use this software. It's not very easy to work with that. It's WX Maxima, so it's a free source software. It's almost the same as mathematical. You can find so many options here to do, as well as the plot of the functions, for example, and whatever. So For example, you can plot every functions here as you want. For example, tangent x, for example. Anything you can plot here. Of course, there is something here where I don't know. That's software error. Okay, let's see. Okay, we have problem here with that, but I didn't use this long time. But anyway, there is a software that maximum is free to do. There is a grapher here if you have a MacBook. So grapher is a free software. Also, you can plot any functions as you wish. For example, you can give classic function, for example, two-dimensional. So give the function and then it will be plot for you. Okay, X, I think it's working or not. Let's just see. See, that's everything you can. There is some software for plotting. So for plotting, you don't need to be worried. All right, remaining two slides. I want to share these two slides, and then we will close these today's lectures. So fusion cross sections, we talk about it, but we never say that what is sigma. Sigma call it reaction cross section. Reaction cross section is related to the energy. If the particles are more energetic, you expect that probability of the reaction cross section will be increased or so. So cross section for nuclear is calculated by nuclear physics methods. You can calculate the cross sections as a function of energy. This is the function. SAE is a function which you can calculate from nuclear and physics techniques. But actually, what you see here is the gamma factor. If you remember, gamma factor times some parameters to give the meaning of the cross section to these equations. Okay. These cross sections which we obtained here is based off the Coulomb barrier models. So we use the penetrations or the tunneling equations, and that is the reason you have this factor here. If the energy of particles are very low, so then the fusion cross section will be proportional to the square of the Dobroi wavelengths. But if the Dobroi wavelengths is proportional to the inverse of the momentum, and because momentum is related to the kinetic energy, so Dobroi wavelength square will be proportional to the inverse of kinetic energy, and that is the reason you have here 1e here in the fusion cross sections. This factor of 1/e, actually in previous slide, this e 1/e came from this consideration for the low energy cross sections. The product of when the fusion reaction happened, there is a function we call it S factor. So S factor is a standard expressions, and it is very much difficult actually to find this S factor. But I want just to say that S factor is a weakly independent on energy. I mean, if the energy increases very much, S doesn't change very much. So let's go and try to plot this function and see what's going in this function. So let's just, I consider EG over G as a parameter X here in our model, okay? So what I want to do as a last things today is that just plot this function and see what's going on here. As I told you, you don't need to be worry about the S, so we consider S as a constant. Let us take S as 1 or very tiny numbers. So what I want to plot is that this is sigma, for example, as a function of E. So I take S as a E, E as a X, I mean, just to not be confused. And here you have exponential, exponential of what? Exponential of minus EAG. EAG, I take B, for example, Bx square. All right. So this is my functions. So let's go. I want to plot this function for several regimes of the, or for the different, I want to plot this for 3D, for example, plot of these functions, sigma, when the range of the x, x is started from 0 to large number, for example. X is the distance between the source to the target. And then I take a b. B could be any parameter. B could be from, for example, 0.1 up to the, I don't know, for example, 4. Then let's see. So this is a very tiny number. So it's trying to plot for you this function, but let's see. You see? So this is the graph, it's a very nice graph. So it gives you the reaction cross sections versus the 3 parameters. You see up to the sum, x, so this is the x from 0 to 10. Up to somewhere, the probability will be increased. Look, increased, and then they decrease it, and somehow it will reach the constant value also, especially. But it depends to the parameter of the b also. But if you fix the b, if you fix the b, if I fix the b, I mean, if I do one thing, I fix the b as this number, for example, and then I plotted this. Then I plotted this versus the x. Let's see what's going on. This will be, so this is that the function is very weak, actually. The function will be important only the SAE as a function of E, I mean X here will be important only in the very low energies, as you see, in very low energies. Or can I plot this? At very low energy, it's almost 0, the reaction cross section. Del will be increased up to the maximum, and then will be decreased. Anybody know how to find the maximum here? How we can define the maximum? You can get the coordinate of this, so the maximum reaction cross sections will happen when the particle is in the distance 0.13 in the bonds, for example, and it reached the maximum 4.3, as you see here. 4.3, 4.35, for example, is the maximum reaction cross sections. What is the total maximum? What is the total cross sections? So total cross section, you can take the integral from the what? From the sigma, from the fine function which is called sigma, from 0 to infinity. So then I can write it here, sigma x from 0 to infinity. Let's just see that it can calculate this or not, and you have the sigma as a function of x. Just waiting, it cannot do that because it says that it is diverging from here. So let's let it not to diverge. So this, the integral cannot be calculated then. I mean, the total reaction cross section is difficult to calculate. I mean, the area under the graph. I want you go and find this for me, how to calculate the total fusion cross sections, reaction cross sections as a function of energy. I mean, this is your function, sigma E. Make the integral of sigma E from the lowest energy to the maximum energy. The lowest energy is EG, I think, is the EG. So let's go and find for me the integral from the lowest energy to the maximum. I mean, try to calculate this integral by any methods which you know. Maybe I will give you that as next homework also. Who know that? So what I say in my lecture, please go through that. Find the total reaction cross sections for a given range of the. You see here we consider S as a constant, but S is determined by nuclear physics. I want you go also to study how to calculate these S factors. Okay. All right. I stopped the lecture here, so I don't want to make more pressures. So I stopped the recording here.